Good morning to all of you. Today we will continue with our discussion on electrostatics. So, today we are going to discuss a very important law in electrostatics, and that is Gauss's law. Gauss's law relates electric field and charges, and for this we would need to introduce the concept of flux. So, this flux actually comes from the word, it means flow in Latin. So, first we will introduce the concept of flux, and I will show you that Gauss's law relates electric flux and charges. So, to introduce the concept of flux, let me consider a fluid flowing with a uniform velocity. So, I can take for example, the fluid is flowing like this. Say let me assume that this is x, this is y and this is z. So, let me assume the fluid is flowing along the y direction. I take a surface like this, say of some length L and width L, and this frame is placed perpendicular to the flow direction. So, the liquid is flowing along the y direction and this frame is parallel to the xz plane. So, the fluid is crossing this surface and moving from left to right. The question I ask myself is, what is the volume of fluid crossing this surface per unit time? What is the volume? So, the fluid is flowing through the surface. So, how much volume of fluid is flowing per unit time through the surface? Now, if I look at the fluid flowing through the surface, so here is my surface, fluid is flowing like this through the surface. Now, you see if the surface area is S, and the velocity is v as I wrote, then how much fluid will cross, how much volume of fluid will cross? To understand that, let me take a length equal to v from here. So, this length is v. So, there is a imaginary plane I consider at distance v from the surface. This is my actual surface through which I am trying to find out the rate of fluid flow, and I consider an imaginary surface at a distance v from this surface. Now, as the fluid flows, remember the fluid is flowing with the velocity v. So, this surface after a unit time would have come and into the surface. So, this surface I attach, with that surface I move with the fluid, and in a unit time this surface, the back surface would have come and coincided with the front surface. So, what it implies is all the fluid contained within this volume would have crossed the surface in a unit time. So, volume rate of flow will be the volume contained in this the volume of fluid contained in this volume, and what is the volume of this? The surface area into this length. So, that means V into S. So, this is called flux. Flux of fluid flow through this area is velocity times the surface area, and in this case I am considering the area to be perpendicular to the direction of flow. So, this implies that V times S volume of fluid is flowing crossing this area per unit time. Now, that is an area perpendicular to the flow direction, but suppose my area was not perpendicular to the flow direction, suppose the liquid was flowing like this and my frame happened to be at an angle. So, this subtends an angle theta. So, this is my frame now. I have inclined the plane, the frame, the same area I have inclined, and now you see that the rate of flow will change, because imagine the limit when this frame becomes parallel to the direction of fluid flow, no fluid will be crossing the area, because they are all flowing parallel to the area. So, now how do I calculate this? So, let me look from this side. So, I have this line, this is my vertical, this is theta. So, I can take a point which is at a distance v from here, this is my area S. So, all the fluid within this volume, so this is also v, all the fluid contained in this volume would have flown through the surface in a unit time. Just like in the earlier case, the fluid which was lying at a distance v from the surface would have crossed the surface in a unit time. Here also all the fluid contained within this volume would have crossed the surface, and the volume of this fluid now is nothing but v times S cos theta. This is S cos theta and this is v, that is a parallelogram, and its volume, its area is v s cos theta multiplied by the other dimension. If you multiply by the other dimension, this dimension, then you will get the volume which is v s cos theta. So, this is now the flux is v s cos theta. This flux is reduced because this area is now projected with a smaller area as far as the fluid flow is concerned. So, this area is inclined to the fluid flow. So, although the area is S, the fluid is actually only crossing through this area which with its projection. So, if you see, if theta becomes 90 degrees, cos theta becomes 0 and the flux becomes 0. So, if the fluid is flowing like this and your frame happens to be like this, obviously there is no fluid crossing the surface, it is just grazing the surface and going away. So, the flux depends on the angle between the surface and the direction of fluid flow, and the flux happens to be v s cos theta. Now, what is v cos theta? V is this direction and theta is this angle. So, if I draw a normal to the surface, this vector is perpendicular to the surface, this line is perpendicular to this line. So, this angle is also theta. So, this is nothing but v dot n into S, because v dot n is v cos theta, n is the unit normal to the surface S, and so v dot n S is the flux now. So, this tells me that the flux now, flux of fluid flow depends on the angle made by the surface with the direction of the fluid flow. Now, I can write this in a more compact form by introducing what is called as a vector area. So, if I have an area, if I define an area like this, suppose the area is S and this is the direction of the normal to this area, I define the vector area S vector is equal to S times n cap. Vector area is a vector whose magnitude is equal to the area of the surface and whose direction is the normal to the surface. Of course, for a surface like this, whether I choose this normal or that normal, there is an ambiguity, but later on we will be discussing closed surfaces in which this ambiguity is resolved. So, a vector area contains not only the magnitude of the area, but also the unit vector perpendicular to that area. So, the vector area not only gives me the area, but also its orientation. For example, if I take an area, suppose I have the 3 axes like this, x, y, z. If I take an area here in the xz plane, its normal will be pointing like this. So, if the area is this is vector area will be S times j cap. If you take another area, the same area, and put it in another direction, say for example, I put it like this area S, this is I cap. So, vector area here is S into k cap. So, the magnitudes of these areas are equal, but the directions are different, and that is contained in the unit normal. So, vector area is a very useful concept that you will be using in many different subjects, but this vector area contains not only the magnitude of the area, but also the direction of that is the direction of the normal to the area. So, what we now like to do is I would like to calculate what is the flux. So, although I have introduced the flux as the flow of a fluid, this flux concept can be generalized to all vector fields. So, I can define an electric flux with respect to the electric field vector. We know that electric field is a vector, and so if you have for example, a surface like this of area S, S vector is like this, and if the electric field is pointing in this direction, if it is uniform electric field, I will define the electric flux phi as E times S. Actually, it is E dot S, where S is the vector area and E is the electric vector, and so E dot S is nothing but, because in this case E and S are parallel, E dot S is E times S. So, that is the electric flux. In the case of fluid flow, there was actually a fluid which is flowing through the surface, but in the case of electric field there is nothing which is flowing. I have extended the concept of flux to a vector field like electric field. So, I can this will give me what is the something like the number of electric field lines crossing the surface area, but this is there is nothing flowing in the electric field case, it is simply represents a quantity. So, now let me try to calculate. I am more interested in a calculation in which I want to see what is the flux crossing a closed area. So, I am taking a closed surface which is closed. So, as an example, let me take a cube of side L, cube of side L. So, this cube has, and this cube is oriented along the xyz axis like this, which I have shown, and let me assume that I have a constant uniform electric field. E vector along the y direction. So, my electric vector is pointing like this along the y direction, it is supposed to be uniform. So, I want to calculate what is the net flux of electric field passing through this closed surface. This is the closed surface, as you can see here, it is a cube which I am taking as an example, and the cube encloses a volume and the cube is a completely closed surface. Now, although the normal to the surface was ambiguous in the earlier case, here we always define the normal to be the outward normal. So, outward means a normal direction which is pointing out of the volume. So, for example, on this surface the outward normal is in this direction, on this surface the outward normal is up, on the bottom surface the outward normal is downward, on the side normal the normal is here, and on this surface the normal is on the other direction, and behind the normal is like this. So, there are 6 surfaces and 6 normals, and all the normals are taken to be outward normals. So, I want to calculate what is the net flux of electric field through this volume, through all the surfaces. So, what I will do is I will calculate the net flux through this surface, through this surface, through this side surface here, and through the back surface, the top surface and the bottom surface. So, there are 6 surfaces. We will individually calculate the flux of electric field crossing each and every individual surface, add them up and get the total flux. So, let me start calculating the flux, and let me show you some slide. So, in the slide, as you can see here, this is the cube, this is the electric field which is pointing along the y direction. So, the electric field is E naught j cap, these are the electric field lines, and this is the cube, the same cube shown with all the surface normals. So, the normal to this surface which I have called BCHG is along the x cap direction, I cap direction. The one which is behind, which is ADIF, is minus S I cap because it is in the minus x direction. The top surface GHIF has the normal along the k cap direction. The bottom surface BCDA is minus k cap direction, and similarly this surface HCDI has plus S j cap direction, and this back surface GBAF has minus S j cap direction. So, these are all the 6 surface normals. So, I need to calculate what is the flux crossing each one of these surfaces. So, let me calculate on this sheet of paper here. So, let me consider the surface. So, let me draw the figure here. So, I have this cube, x, y, z, and so electric vector is E naught j cap. So, plus let me calculate what is the flux through this surface. So, this surface has a unit vector which is j cap. So, this and of area S. So, let me call this flux phi 1. Let me use the same indices. This is called B, C, D, A, and this is G, H, I and F. So, this is the flux F 1 is through surface H, C, D, I. So, this will be E dot S, which is E naught j cap dot S j cap, which is nothing but E naught times S. The surface is S j cap, electric vector is E naught j cap. So, the flux through the surface is E dot S. So, E naught j cap dot S j cap, which is E naught times S. Now, what is the flux through the back surface? That is this back surface. So, this is AFGB. This is equal to again E dot S, which is equal to E naught j cap. Now, remember the back surface has a unit vector which is S times minus j cap. So, this is equal to minus E naught S. So, you can understand that the flux is negative because the surface area is pointing towards minus j cap direction, the electric vector is pointing towards plus j cap direction, and the dot product of these two is minus E naught S cap S. We can similarly calculate the flux through the remaining surfaces. So, let me take one more example. So, flux through let me calculate the flux through the surface, which is B C H G. So, this is equal to, let me call it phi 3, which is equal to E dot S, which is equal to E naught j cap dot. Now, S vector is what? Let me see here. So, this is S and this S vector is actually S times I cap, because this normal is pointing towards I cap direction dot S I cap, which is equal to 0, because j cap dot I cap is 0, j and I are perpendicular to each other. So, that is 0, and you can again understand this, because as I mentioned before, the electric vector is pointing along the y direction and the surface is actually the y direction is parallel to the surface. So, there are no electric flux lines crossing this surface. So, similarly you can show that the flux crossing the back surface, the bottom surface and the top surface are all equal or equal to 0, and so the total flux is nothing but the sum of these two, and that happens to become equal to 0. So, total flux for this example, total electric flux is equal to E naught S minus E naught S, which is equal to 0. So, there is no flux, electric flux crossing through this is 0. Please note, electric field is not 0, electric field is finite, it is uniform, but it so happens that the amount of electric field lines entering one surface is equal to the electric field lines leaving the surface. So, this particular flux is from the front surface here, this flux is from the back surface, and they are equal to each other and opposite of each other, opposite sign, and so the total becomes 0, and there is no flux entering the remaining 4 surfaces, and so the net flux becomes 0. So, I can actually calculate using this flux formula what is the flux of a vector field through any closed surface. Now, let me show you another slide. So, in this case I had a cube which was exactly oriented with the axis. Now, let me take a situation where the cube, let me show you the slide in which the cube is now not placed along the axis, but inclined. So, I have rotated the cube around the z axis, so that the line AB makes an angle of theta with respect to x axis. So, now I need to again, I want to again calculate the total electric flux. So, for which I need to draw all the surface normals. So, here is a slide which shows you. So, the front surface, which is shown as red here, has an electric flux pointing, the surface area is pointing in this direction, theta is the angle between the x axis and this plane. So, we can write the surface area vector for this surface, similarly the area vector for this surface, which is exactly opposite of this vector, because it is in the opposite direction, the area vector for this surface, the area vector for the back surface, the area vector for the top surface, and the area vector for the bottom surface. So, this for example, this vector you can see, but this line is parallel to this line here, and so this makes an angle theta with the x axis. So, this unit vector has a component cos theta along x direction and sin theta along the y direction, and that is why the area vector is given by this. The magnitude of this vector is same as S, and the direction is given by I cap cos theta plus j cap sin theta. So, I can actually find out the unit vectors of all surfaces, and then from these unit vectors I can calculate the total flux. So, for example, let me calculate the flux through the front red surface, which is shown in the slide. So, the electric flux now I have gone back to the surface B C H G, that is this surface here, front surface, and let me show you the slide in the slide here. So, this is, let me call this phi 1, which is equal to E dot S, which is equal to E naught j cap dot S into I cap cos theta plus j cap sin theta, which happens to be equal to E naught S sin theta, because j cap dot I cap is 0, this flux becomes E naught S sin theta. The flux through the back surface, which if you see the slide here, this back surface, no, the flux through A d I f, which is exactly the surface opposite to the surface. In the slide you can see the area vector. So, phi is equal to E dot S, which is equal to E naught j cap dot S into minus I cap cos theta minus j cap sin theta, which is equal to minus S into E naught sin theta. So, you got the flux through the back surface. Similarly, you can calculate the flux through the remaining surfaces. The flux through the top surface will be 0, the flux through the bottom surface will be 0, and the other two fluxes, let me write down the expression here. The other two fluxes will be, if I call this phi 3 is equal to, so if you look at this this surface, the surface which is shown blue in the slide here, if you can see the slide, it is shown as the blue surface here, and that is through that is E dot S, which is E naught j cap dot S into minus I cap sin theta plus j cap cos theta, which is equal to E naught S cos theta. And finally, the flux through the surface which is opposite to this surface is E naught E dot S, which is equal to E naught j cap dot S into I cap sin theta minus j cap cos theta, which is equal to minus E naught S cos theta. And flux through top and bottom surfaces equal to 0, because the normal, the surface normals or the surface areas are perpendicular to the direction of electric vector. So, we have got 4 fluxes through. So, you have flux through the 4 surfaces, one is E naught S sin theta, the other is minus E naught S sin theta, one of them is E naught S cos theta, the other one is minus E naught S cos theta, and you can now see the total flux will be the sum of all these 4 fluxes, and that happens to be again 0. So, E naught S sin theta minus E naught S sin theta plus E naught S cos theta minus E naught S cos theta, which is equal to 0. So, the flux crossing each surface has changed, but the net flux is still 0. So, this is the technique to calculate the flux through any closed surface. I look at the normal to the closed surface and then calculate E dot the area vector for each of these areas, and I will get the total flux. So, now we will come to Gauss's law. So, once having defined electric flux, electric field flux, now let us look at Gauss's law. So, as an example, to calculate electric flux, let me consider a charge q, and let me take a sphere around the charge, sphere of radius r. So, this is a sphere of. So, my problem is to calculate what is the electric flux crossing the surface. What is the electric flux crossing this sphere because of the point charge placed at the center of the sphere. Now, what is the electric field generated by the point charge? We know this 1 by 4 pi epsilon 0 q by r square into r cap, where r cap is this direction and r is the distance from the center. So, this is the electric field at any point at a distance small r from the charge, and r cap is the unit vector from the charge pointing out like this along the radial direction. Now, I am assuming a positive charge here. So, the unit vector, the r vector r cap is along this direction. Now, to calculate the total flux through the sphere, I must know the area vector. So, for example, at this place the area vector will be pointing like this, at this place the area vector will be like this, at this place the area vector will be like this. They will all be radially pointing away from the center. It is a sphere. So, the area vector of any patch of the sphere will be pointing away from the center, and so this will be the area, these will be the directions of the area vector. So, what you can see is, unlike the example before, the area vector, the area direction of the area vector keeps on changing as you move along the surface, but at all points the area vector is along the line joining the center to the center of that area vector. Now, as you can see here, the electric field is radial along the line joining the charge to this, to the point on the sphere, and at that point. So, suppose I want to calculate the flux through a small area here. This is the electric field direction, and the area vector is also in the same direction. So, what I need to do is, because of a surface which is not flat, what I must do is I must take a small area here, a small area ds vector, then I calculate, I know the electric field at that point. So, I calculate the small flux through that, which is E dot ds. So, ds is a small area, ds vector is the small area vector, E is the electric field at that point. I calculate E dot ds there, that gives me the flux through this small area. So, I calculate like this, I divide the entire sphere into areas at around all around the place and add up all the fluxes to get the total flux. Now, as I mentioned, at every point the area vector points along the direction of the electric vector, because electric vector is radial and so is the area vector, because the charge is located at the center of the sphere. So, E and S become equal in the same direction. The other thing I notice is that electric field across all the points on the sphere is the same, because the charge is centered at the at the center of the sphere. The electric vector, electric field at all points on the sphere is exactly the same, and electric field on the sphere will be the magnitude will be 1 by 4 pi epsilon 0 q by r square. So, electric field is the same at all points on the sphere. The electric vector is parallel to the area vector at all points on the sphere. So, the total flux will be electric field into the area of the sphere, because electric field is the same at all points on the sphere. So, the total flux will be electric field into 4 pi r square, which happens to be q by epsilon 0. So, if you have a point charge placed at the center of a sphere, the net electric flux flowing through the sphere is q by epsilon 0. That is a statement of Gauss's law. If you have a point charge at the center of a sphere, then the total flux, electric flux crossing the sphere is q by epsilon 0. Now, what will happen if the surface which I am considering, let me take the same point charge, but a surface which is not a sphere. So, the problem would be what will happen to the flux. So, I want to calculate the flux through a surface which is not a sphere. So, I have the point charge here, this was the sphere which I drew earlier, and I have some arbitrary surface. So, let me show you a slide here. In the slide I am showing you a charge placed at the center of a sphere. In the slide you can see the center of the sphere having a charge. So, this is the sphere here which I am drawing as S1, and there is some arbitrary surface here which I am calling S2, and these lines represent the electric field lines from the point charge. They are all radial pointing away from the point charge. So, I take a small area here and I draw the electric field lines crossing that area. Now, as you can see here, these lines, the electric field lines come out and hit the other area, the S2 surface, over some other magnitude of area and orientation, Please remember, this arbitrary surface has its normal at every point in different directions. So, here I have drawn a small patch having its area vector shown as an arrow here. The area vector on this surface of the sphere is along this direction, because this is the center of the sphere, and electric field is also parallel to it. Here the electric field is pointing like this and the area vector is pointing in some other direction. So, I need to calculate for the flux. Through this I had simply multiplied the electric field by the area. Here I need to remember that this makes an angle. So, I will have to calculate the dot product of this electric vector and this area vector. Now, as you can see here, if I imagine electric field lines coming from the point charge, all those lines which are crossing this small area here will also be crossing the same area here. Although this area is larger, it is oriented in a different direction, and so its projection will be along a direction perpendicular to this electric field line, and as we discussed before, I will have a component ds cos theta, and if I can imagine electric field lines starting from the point charge and moving out, the number of electric field lines crossing this area on the sphere will be equal to the number of electric field lines crossing this area on the arbitrary surface. So, I can extend this argument, and for every patch of area on the arbitrary surface, I can make a projection back to the point charge, and that projection will intersect the sphere in a small area. And so, what I will see is, for every area on the arbitrary surface, I have a small area on the sphere, and they will have the same flux of electric field passing by. So, what this argument implies is that the net flux crossing the sphere is exactly equal to the net flux crossing this arbitrary surface area. You can also imagine this by understanding that these are electric field lines. All the lines which are emanating from this point charge, which are crossing this surface, spherical surface, will also be crossing this other surface area, and so the net flux of electric field through the arbitrary surface is the same as the flux through the sphere, and the flux through the sphere we have just calculated as q by epsilon 0. So, if I come back to the slide here, as we see, the point charge has the flux q by epsilon 0, whether you take the sphere or an arbitrary surface surrounding the point charge. So, this is the generalized Gauss's law. So, Gauss's law states that the flux through an arbitrary surface which encloses this point charge q is q by epsilon 0. So, this implies essentially that whether the point charge is at the center of the sphere or anywhere, if you put the point charge here, even then the flux it will be q by epsilon 0. This is point charge q. Irrespective of where you put, the net flux will be 0, sorry, q by epsilon 0, and independent of position of this charge, because this will appear like an arbitrary surface surrounding this point charge. Now, what will happen if I have more charges? So, suppose I have a charge q 1, another charge q 2, the total flux will be equal to q 1 by epsilon 0 because of charge q 1 plus q 2 by epsilon 0 because of charge q 2. If I have another charge q 3 plus q 3 by epsilon 0 because of charge 3, etc. So, this will be nothing but sigma q I by epsilon 0, which is equal to q by epsilon 0, where q is the total charge enclosed by the surface. So, let me write it again here. So, if I had a number of charges q 1, q 2, q 3, etc. So, if I consider any surface A S, so total electric flux is equal to the sum of the charges, all the charges inside by epsilon 0, which is sigma and this sigma q I is charges enclosed by. And that is Gauss's law. So, Gauss's law states that if you have any surface which surrounds a set of charges, the total electric flux crossing that surface is equal to the sum of all the charges present within this enclosed by the surface divided by epsilon 0. This is a very, very important law, and this law is used to solve problems in electrostatics, especially when you have certain kind of symmetries in the problem. As I will show you through examples, it is very easy to use Gauss's law to calculate electric fields, or if I know the electric field, in certain situations I will be able to calculate what is the charge distribution. So, what this Gauss's law states, it tells me, is the relationship between the electric flux crossing a surface and the charges enclosed by the surface. Now, I must mention a couple of points here. In this Gauss's law, these are the charges enclosed by the surface. So, suppose I have a surface, suppose I have q1 one charge here, another charge q2, another charge q3. The total flux is equal to q1 plus q2 by epsilon 0, because q3 is not enclosed by the surface. Q3 is not enclosed by the surface. So, as you can see here, the electric field lines will go like this, and as we saw in the case of cube, what will happen is there are field lines entering the surface, and there are also field lines, same field lines will leave the surface. So, the net flux, because of the charge lying outside the volume enclosed by the surface, will not contribute to the total flux. So, in this flux equation, phi is equal to charge enclosed by epsilon 0. So, in this flux equation, we are only adding up the charges which are enclosed within the surface or by the surface, and any charge lying outside the surface does not contribute to the flux. At the same time, please remember that the electric field at any point is the sum of the electric field produced by all charges, whether inside or outside. So, the electric field here will consist of electric field because of q1 plus electric field because of q2 plus electric field because of q3. The flux which is crossing this will only depend on q1 and q2, because q3, the flux from q3, actually the amount of flux entering the surface because of q3 will be equal to the electric flux leaving the same surface. So, q3 does not contribute to the flux, while q1 and q2, which are enclosed within the surface, are actually contributing to the flux. So, we must remember that electric field at every point is determined by all charges present in the system, while the flux through any closed surface is determined only by the charges enclosed by that surface. So, this particular law is valid for any arbitrary surface, and is useful in situation where there is symmetry, as we will discuss later. As an example, wherever there is symmetry in my system, I can use this law to find out the electric field because of a charge distribution. In some situations, I can use, in the reverse case, when I have an electric field, I know the electric field, I can use that to calculate the charge distribution. Also remember that this law is based on the inverse square law of Coulomb's inverse square law. Like in the example of a charge at the center of a sphere, which I calculated, the flux in this, remember we had done, the electric field was varying as 1 by r square, the area was increasing as r square. So, the flux is independent of the radius of the sphere. So, whether you take a small sphere or a big sphere, the electric flux remains the same. Now, this is based on the fact that electric field goes as 1 by r square, the inverse square law. If the electric field was not following the inverse square law, then the flux would have depended on the radius and the things would have been very different. Also remember that because the flux law depends on inverse square law, all vector fields which follow the inverse square law will satisfy a Gauss's law. So, gravitational field which also decreases as 1 by r square will also have a law which is similar to Gauss's law, will also satisfy a law similar to Gauss's law. Now, let us use some of this discussion to look at some examples. The first example I want to see is conductors. So, we saw earlier that a conductor is a medium in which there are free electrons which can flow, and because of this in a static situation there can be no electric field within the conductor, because if an electric field existed within the conductor, that will push the electrons, that will force the electrons to move, and I will not be in a static situation. So, once I have reached equilibrium, there can be no electric field, no electrostatic field within a conductor. Now, suppose I consider the following problem. I take a conductor, a solid conductor, and put some extra charges into the conductor. So, these are called excess charges. These are charges beyond the electrons and protons that present in the conductor, that are present in the conductor. So, I put some extra charges. Now, the question arises, where are these charges sitting? Are they inside the volume of the conductor, or are they on the surface of the conductor, or are they in both places? So, we will use Gauss's law to solve this problem. So, now I have a conductor in which I have thrown some excess charge. So, I throw a charge q, some excess charge q into the conductor. So, the question is, where are they sitting? Now, from my earlier argument, in an electrostatic situation, E must be 0 inside the volume of the conductor. There is no electric field inside the conductor. So, what I do is, I take a surface inside the conductor, I take a sphere inside the conductor, the entire sphere is inside the conductor. Now, this is called a Gaussian surface. To employ Gauss's law, I consider a surface, an imaginary surface of any arbitrary shape which suits me, which is called a Gaussian surface. So, in this case I take a sphere, for example, the sphere encloses the entire conductor and I want to apply Gauss's law. So, first thing is, the electric field at all points on this must be 0, because there is no electric field within the conductor. So, the net flux must be 0, because net flux is equal to charge enclosed by epsilon 0, and because the electric field at every point on the surface is 0, the net flux crossing the surface is 0, and that means the net charge enclosed by the surface is 0. Now, please remember, when we calculate the net flux, we have to be aware that the charges can be negative or positive. So, for example, if I take a positive charge at the center of a sphere, the flux will be q by epsilon 0. If the charge is negative, so here the electric field lines are going like this. Here, if it is a negative charge, the electric field lines are moving inside. So, the flux will be minus q by epsilon 0. If I take a situation where I have a plus q and a minus q, for example, a dipole, and this is my surface, the net flux will be 0, because plus q by epsilon 0 because of this. So, we have seen the electric field lines like this. As many electric field lines will come out as will get back in. So, the net flux, because of the presence of these two charges, becomes 0, and that is because the total charge enclosed by the surface becomes 0. So, in flux calculation I must keep track of the sign of the charges. So, let me come back to the conductor. Here I am taking a Gaussian surface and I find that electric field at every point on the surface is 0. So, the net flux must be 0, which implies that the charge enclosed is 0. Now, I reduce the radius of the sphere to smaller and smaller values. The electric flux continues to be 0 until I reach almost a point, which means that the charge enclosed by that sphere is always 0 no matter what the size of the sphere is, which means that there can be no excess charge within the conductor. So, I can take the sphere at different points on my conductor wherever I want, and I find that the net flux enclosed by this sphere is 0, by this sphere is 0, by this sphere is 0, by this sphere is 0. So, and because the net flux is 0, and that is because electric field is 0, and I can reduce the size of each sphere to smaller and smaller values until I reach a point, there can be no charge inside the volume of the conductor, no excess charge. So, all it implies is whenever you put an excess charge on a conductor, all the excess charge remains on the surface. So, by excess charge, as I said, the charge which we add to the conductor, these do not include the electrons and protons which are part of the material of the conductor. So, here is an example where I have used Gauss's law to find out whether there are charges within excess charges within the conductor, but which means knowing the electric field to be 0, I have argued using Gauss's law that there can be no excess charge within the volume of the conductor. All the excess charge that you put will be sitting on the surface. So, that is an interesting result that I get by using Gauss's law. So, here is this was an example where I used Gauss's law to calculate the charge distribution from a known electric field distribution. So, electric field was 0 inside, so that gives me no charge inside. Now, let me take another example. So, let me take a sphere, conducting sphere, with charge plus q. So, here is a sphere, it is a solid sphere, and I put charge q on this. Now, from my earlier argument, all this charge must be sitting on the surface of this conductor. There can be no charge inside the conductor, all this charge is sitting on the surface of the conductor. Now, symmetry plays a very important role in many of these problems. So, the question is, when I put the plus q charge, excess charge on the conductor, where is it on the surface? So, first thing is, from Gauss's law I have shown that the charge must be residing on the surface, it cannot be within the volume of the conductor. So, where is it sitting? Now, if you see, a sphere is completely symmetric, there is no preferential point anywhere on the sphere, which means that the charge must be equally distributed everywhere across the sphere, on the surface of the sphere. There cannot be any point on the sphere which has little more charge, because all points on the sphere are equivalent to each other. So, when I put a charge plus q on the sphere, that will be distributed uniformly right across the surface of the conductor, and so this charge will generate a surface charge density Remember, I had called it sigma before, q by 4 pi r square. R is the radius of the sphere. So, the charges are all sitting on the surface of the sphere as a surface charge density q by 4 pi r square. Now, I want to calculate what is the electric field produced by this conducting conductor with an excess charge plus q, which is uniformly distributed on the surface. What is the electric field that this conductor will now produce as far as outside region is concerned? So, I will now use again Gauss's law. First thing I could have, in principle, I have to solve the problem by taking every charge on the surface of the conductor, calculate the electric field at a point. Suppose I want to calculate the electric field here, I must take the charge here, find out the electric field from here, what is the electric field from here, what is the electric field of this point from here, and so on. All the electric fields I must add at this point to calculate the total electric field. That problem becomes little more involved. We can use Gauss's law to calculate the electric field of this charged conductor. So, this I will discuss in the next class, where I will calculate what is the electric field produced by this conductor, which is a spherical conductor in which I have thrown an excess charge capital Q, and we will use Gauss's law and we will see how the calculation becomes very simple. I would like to end the discussion here with one problem for you to think about. So, let me consider a plus q here, a minus q here, a minus 2 q here, and a plus 2 q here. So, I draw two surfaces, this I call S1 and this I call S2. So, first is calculate the electric flux through S1 and S2. 2, draw a closed surface through which flux is A maximum and B and negative, and another one is positive and maximum. So, I want you to draw surfaces, Gaussian surfaces through which the flux is positive and maximum, a surface in which the flux is negative and maximum. Thank you very much.